Well, unfortunately, once in a while I need some evidence that you're in class, so will you please initial the first column, and I'll need it at the end of the hour. Well, we're in the middle of digital filters. When digital filters first arose, most of the old analog filter people thought it was the same old stuff. They did not see anything new. The same thing happened in the history of computing. In the early days of computing, it must have been 1,000 times I heard somebody say, computing, there's nothing new in it, there's nothing you can't do by hand except it's a little bit faster. Well, yes and no. Those who thought that computers were nothing other than just plain old hand calculating, speeded up, never made a contribution to computing. Those who made contribution to computing believed that computers were something new. Same on digital filters. Now I need to introduce the idea of the order of magnitude. An order of magnitude means a factor of roughly 10. And I assert that in almost all fields, a factor of 10 means fundamentally new effects. For example, if you increase magnification by 10, in biology you'll find new things. If you can see 10 times further out in space, you will find new things. To bring it down to your own experience, consider you can walk at about 4 miles an hour. And with horses you could do a little bit better, but let's consider that. Where could you go for a vacation walking from your house? Not far. Automobiles you drive typically 40 miles an hour. Maybe go more or less. You can now, with an automobile, go a great many places you cannot go by foot. I know of one person I ever met who walked across the United States. Many of you have driven across it. Airplanes fly at around 400, 500, maybe something like that. Again, 10 times faster. With airplanes, where you go for a vacation is greatly increased. I assert each single factor of 10 in transportation speed has changed radically what you can do. Computers have done a factor of 10 to the 9th now. I read a blurb today. Some machine is going to do, at best, something like 6.4 billion floating point operations a second. Well, you couldn't do 1 in 20 seconds, roughly, with a desk calculator, day in and day out. So it's been an enormous change. Well, now, the people who didn't recognize something was different in digital filters didn't do much. The first digital filter I met was with John Tukey, smoothing by average of 3s. And you remember a running average of 3 looks something like this out to f equals 1/2. A smoothing average of 5 went like that. Now, if I'm going to take one followed by the other, I'm going to get the product. I now have 3 zeros. And you can see the product there is going to be much less. It's going to be 1/15, something like that. So the product, smoothing by 3s followed by smoothing by 5s, is going to remove the upper half of the frequencies and leave only lower half, which is what we call a low-pass filter. Very, very simple filter with very, very simple equipment. Just running average of 3 followed by running average of 5, and in fact the 15 is carried over to the last minute. Now I'm going to have to work in, I told you, rotations. Radians is what you learn in calculus. Radians divided by 2 pi will give you rotations. And the Nyquist business of last time was in rotation from -1/2 to +1/2. Now most of you have had some knowledge of digital filters, but it may cause you wonder, how is it that a digital filter actually does its filtering? What do I mean by it? You're used to an analog signal and it can be removed, but how does a digital filter work? Well, I'm going to show you by taking the simplest digital filter I can and designing it and then showing you it in action so you'll see how it happens. So you'll be convinced that it really does what it says it's going to do. Well, I'm going to pick a filter. YN is A un minus 1 plus b un plus a un plus 1. For smoothing, I have to have symmetric. That means I have two adjustable filters. And what I'm going to do, at 1/6, I'm going to require it to be 1. And at 2/6 or 1/3, I'm going to require it to be 0. So the transfer function is going to be something like that, but it's got those 2 points nailed down. I put in e, try un equal e to the 2 pi I f n. And I will get a with an exponential plus and one with a minus. I'll get e to the I 2 pi I f n. I'll get an exponential minus and plus, and I'll get a b, so I'll get b plus 2a cosine 2 pi fn. Okay, here I'm going to put 1 in. Remember, this is the transfer function. I got the original function back out times something. That was what the idea of an eigenfunction was. If I put the frequency in, I get it right back out again. It comes out of every one of the terms, multiplied by something, that's the something. Well, I want to get that to go through this, that. I put the conditions down, and I will come up with some simple algebra. A equals B equals 1/2. That means this filter is 1/2 of Fn plus 1 plus, un plus 1 plus un plus un minus 1. In words, the sum of 3 numbers divided by 2. Now that resembles the smoothing by 3's, except it was not the same thing. It's like it. So that filter, I assert, does this. Does it do it? Let's find out. Let's make some input data. N 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And I'm going to put in 1/6. I will have, if I put a cosine in, I will have cosine 0 is 1, 1/2, minus 1/2, minus 1, minus 1/2, 1/2, 1, 1/2, minus 1/2, and so on. That would be input data. That is data at the frequency required, 1/3. That's, I just made up the data. That is exactly the cosine going in and out. All right. Now I assert that if I take the sum of any 3 and divide by 2, I will get the middle value. For example, the sum of those 3 divided by 2 gives you that. The sum of those 3 divided by 2 will give you that. The sum of those 3 divided by 2 will give you that. All the way down the line. That data will go through the filter and come out exactly the same. It's multiplied by 1. Now if I have this frequency at 1/3, I go through things twice as fast. 1 minus 1/2, minus 1/2, 1 minus 1/2, minus 1/2, 1 minus 1/2, minus 1/2, and so on. If I take this formula, take any 3 of those and divide by 2, I will always get 0, right? Any 3 you want in a row adds up to be 0. That frequency put in comes out multiplied by 0. It's stopped dead. Now let's consider the sum. 2, 0, 0. Minus 1, 0. See, this is 0. This is minus 1, 0, 2, and so on. Now, I assert that in the sum, this frequency should be stopped, and that should come out. Well, take these 3. Add the 3 together, divide by 2, I get this. Take those 3 together, divide by 2, I get that. In the sum, each term is, as it were, separated out. The filter takes, multiplies by its transfer function value, and puts out the result. So I tell you, this simple linear formula breaks the signal up into all possible frequencies, multiplies each frequency by the corresponding eigenvalue, and adds them all back again. And there you see a digital filter in action. It's the simplest one I can build. Now, if you want to take other ones, for example, you want to take the half frequency between the two of them, you will find when you put it in, it'll come up with a value 1/2. Whatever value you had, the output value will be 1/2 as big. If you want to take this one, it's minus 1/3, I think. That's just minus 1/2 or minus 1/3. This is 3/2. If you put in all 1 0 frequency, you get out 3/2 as much, as you can see. So there is a very elementary digital filter in action. It does exactly this miraculous thing. All input frequencies are separated out. Each is multiplied by its corresponding eigenvalue, and they're all added back together again, and that's what comes out. Just like an analog filter. And it's that simple. You merely put numbers in, and out come the results. There's no great problem about it. Now, let's go back now to designing filters more generally. What I generally want is I want to pass some frequencies and I want to stop others. I usually want, this is a low pass filter, I want to pass one out to here. At a cutoff frequency, I want to stop passing, I want to cut those off. That's a low pass filter. I might want a high pass filter. I might want to cut out all the low frequency and pass only high frequency. I might want a band pass, or a band stop, or a notch filter. A notch filter is one, it takes out one frequency. You want that frequency frequently because in the laboratory, 60 cycles is everywhere in this country. In England, it's 50 cycles. And it's everywhere. So you want frequently to build a filter which takes out 60 cycles, removes it. But let me warn you, 60 cycles isn't 60 cycles. It's true that your clock at the end of the day, which is working on exactly 60 cycles, is remarkably accurate. But along the way, it's something different. At our Whippany location, where we got the power from the Jersey Power, down the road a bit, there was a big wax paper plant. And periodically, they start up all those motors. Well, where does the energy come from when they suddenly put the load on the motors? It comes from the flywheel. When the flywheel slows down a bit, then the valves to the steam is opened up a little bit. The motor goes a little bit fast. The generator goes a little bit faster and catches up and maybe goes a little bit ahead. But it has to temporarily slow down. So you may find that the frequencies you have are not exactly 60. They may wander as far as 55 or up to 65. Because if it goes below, it's also got to get above. Because at the end of the day, it's got to average out right, so your clock will be right. But depending on what supply you're getting, it can be quite different. Somebody suddenly puts a load on the thing, it must be that the temporary load comes out of the flywheel. The system cannot respond instantaneously. So when you start removing 60 cycle, look at your thing and see how many other people elsewhere are on that same generator system who may suddenly put a big load on. It'll make a difference. We had trouble with it. We never could get off that line or get them equalized decently, so when it happened, the analog computing had to be abandoned temporarily, and that run was stopped, and we simply started in again. It was a nuisance, but I learned the hard way. Now, if I have two k plus 1 coefficients, I had 3 here, I have k conditions. If I have 2k plus 1, I can put k conditions. All I can do. I can spread them around to do varying things, but there are only k conditions it can meet. It can't do everything. It can't go exactly this curve. It can try. Now what we're going to do is observe the obvious. When I had a symmetric filter, these two terms, one, when I factored out the e to the n, I would have a negative and a positive, so I'll get a cosine. If there's another term out here and here, I'll have a cosine of 2. I'll have cosine. The expansion will be in terms of cosines. If I have an odd function, it'll be in terms of sines. For example, a differentiator. Smoothing filters being symmetric will always give you sums of cosines. Differentiators, which are odd, will give me sines with an imaginary coefficient, but it'll take care of itself in time. So my problem is, how will I get it done? Now I need to look at another story and another moral for you. Michelson of the Michelson-Morley fame, of whom you've heard, was a very good experimenter, and he built once a big machine which would calculate the Fourier coefficients up to the 75 of them, namely 1 for the middle and 37 other frequencies. 75 coefficients in total. Well, the machine, because of the duality that appears between the calculation of coefficients and summing the series, it would also allow him to take the coefficients and recalculate the curve. What does he find? He finds, I'm exaggerating, something like that. He adjusts the equipment for a while, and he's still there. So he mentions in the math department, bad experimentation is your equipment. Mention of other people. Finding Gibbs of Harvard, of Yale, famous Gibbs of Gibbs thermodynamics and so on, says, yeah, of course. I will explain it for you. Let me give you my own explanation first, and I'll give you some sketch of some other reasons why it must happen. The more terms you take, that peak does not go to 0. It gets narrower if you take more terms, but does not go down to 0. It remains around 9% of the overshoot. Well, let me tell you why it has to be. You took a course in infinite series sometime or other, and it said, if the functions are continuous. Well, first let's say not. Let's go back instead to Cauchy, 1850, so 1840, 1830, Napoleon's time. He got in trouble with Napoleon several times. He was trying to put rigor in mathematics, remember, Cauchy. Cauchy's theorem, here, there, and yon, he did a lot of things. Well, he proved a theorem in his book, Volume 1. He never published the rest of them, but because he found too many mistakes in Volume 1. Volume 1 said, if a series of continuous terms converges, the limit function is continuous. But if I take a Fourier series with a discontinuity, I can prove to you that the series will converge, but it clearly converges to a discontinuous function. Both of these were in his book. He never noticed the contradiction. Other people did. They looked in closely and they found this word uniform convergence. Uniform means that no matter where you are, the same delta epsilon will work, independent of the position x. This was done in the 1850s and reported out by several people in the literature, but lost. Gibbs went over the thing again and found it. And this time it stuck because people were ready to hear it. So Gibbs really refound what happened. Now, if I tell you this theorem, this cannot converge. As I think more and more terms, the convergence cannot be uniform, because if it did, the limit function would be continuous. How could it not be uniform? By overshoot. So the argument is basically that phenomena has to happen. Now, you've seen this. If you had an oscilloscope which wasn't really good, when you turned it on, you saw boop and a little wiggle. What you saw when you turned on an oscilloscope for some voltage or other, you saw a little dip like that. Oops. Those wiggles. You saw the Gibbs phenomenon? Because the high frequency had been removed. But unless there's a very good oscilloscope, which is made a point of killing that overshoot, you're in trouble. It's going to be there. Now, I can prove it another way if you want, several other ways, but I think this intuitive one is sufficient for you. Let me go ahead. Our boy Lanchos, he was around this country for a long while, and ended up in Ireland at the Institute for Advanced Study in Dublin. I several times was almost going to meet him. I was going to meet him one time in North Carolina when he was supposed to come over, but he didn't. And by the time I got the Institute for Advanced Study one time, visiting it, Dublin, he was dead. So I never really met him, but he was obviously a very smart guy. He said the following: if I have a Fourier series out to n terms, the wiggles that I see will be like n. They're wiggling about the amplitude of n, or maybe n plus 1, the first one, but it's going to be right out there. He says, well, you know, if I took the Fourier series f of x and integrated from x minus pi over n to x plus pi over n and averaged n over 2 pi, I'll get a smooth value of x. I will average over just a period. So if there's a ripple there, the ripple will average out. Now, it's a matter in the notes, which I don't want to waste your time doing simple algebra. If you take the terms of a Fourier series, remember this n is the same as the last n you had in your Fourier series. That n is the last one there, the size of the ripple. I mean, it's the frequency of the ripple. If you look at any one of the terms, say a sine will go into a cosine, and you put x plus pi over n minus cosine x minus pi over n. Well, the difference of two cosines is twice the cosine of x cosine pi over n minus sine. Well, now I got to divide by n over 2 pi. There's a pi over n there somewhere. And you will find the original cosine is multiplied by sine pi k over n divided by pi k over n. I'm going to call that a sigma factor k involving n, but it's going to depend upon the k. If I do the sine terms, the same thing will happen because of a trigonometric identity. The same thing will happen for the constant term. So lo and behold, a mysterious thing. If I apply this linear operator, averaging over a period to a Fourier series, I get the Fourier series back exact, except to multiply by these sigma factors. And you say, whoa, gee, lucky. Well, yes and no. What were those eigenfunctions? I told you last meeting that they were the eigenfunctions of any linear operation, right? What is that integration? It's a linear operator. There you go, sum of the operator, right? Therefore, that must have happened. If I put the eigenfunctions into that linear operator, I must get them back multiplied by something. And those factors, the sigma k of n, I think, are sine pi k over n divided by pi k over n. And what are they going to look like? When k is 0, it's sine 0 over 0, but you know sine x over x goes to 1. And when x is equal to n, the sign is 0. They look like that. So what are you doing? When you take the Fourier series, if you want to do this averaging, what you do, you multiply by the sigma factors. What do you do there? I let the high frequencies come through accurately, and I let the low frequencies come through accurately, and I more or less kill the high frequencies. Right? That's what I'm doing. That is the effect, just weighting those things. In other words, take the Fourier series, multiplying by this, and that's the new Fourier series, which is equivalent to smoothing by one whole period. I've greatly reduced the overshoot. I've reduced it down to about 1/10 as big. And the first undershoot, I've reduced it even more. These wiggles are enormously killed by that very smoothing process. Well, let me now take some more things. When I have a discontinuity of a function, what should I do with the half value? Well, I suspect when you had Fourier series, you said, oh, you should take the half value, which comes from some method of smoothing. Remember that? Well, I said, if instead of taking all ones and then a 0, because when I have a telescope, the star is shining steadily, I turn the telescope on. When I look, I turn it off, I cut. So what I have is 1, 1, 1, and then zeros on both ends, out to both ends of infinity. Well, I said if I made those n values 1/2, what will happen? So we got to think about this matter. What happens? Well, I'm going to multiply one function by another. If I have a function f is summation a k e to the I omega k, and another one g of x equals summation b k e to the I omega k. When I multiply them together and get ck e to the I omega k, the c's will be turned out to be ck is summation of all the ak's times the b, or am's we'll say, k minus m. Because the sum of the exponents must total k, so the sum of the subscripts must total k. And this, you may remember, is a convolution. Remember? Well, if I've got a thing like this for one function, I'm going to multiply f, the signal coming from the star, by this signal, which is turning the telescope on and turning it off. I will get the convolution. Except that because the c's are 0 outside, this will become summation from minus k to k of the cm, which were all 1s, times the bk. Oh, sorry. Yeah, ck to bk. But the bk's are all 1. So I got e to the I omega k. Result, what you know. Multiplying two functions together convolves the coefficients. And that was exactly my original definition of a digital filter. Digital filter was exactly that. Nothing more. Well, coming back to this, if I put a half in the other way, if I put 1 in all the way through, I will get e to the minus I omega n plus 1 plus e to the I omega n. I want to divide by 2n plus 1 because I've got n plus 1 terms up there. I get a bunch of signs, or alternatively, I got a geometric regression. And since it's symmetric, I've got to turn up with, it'll turn out sine of n plus 1/2 omega over n plus 2n plus 1, oh, n plus 1, n plus 1/2 sine omega over 2. That's what I'll get. Now, what does it say? I'm going to convolve the original signal, which you have, with this function when I multiply by turning the telescope on and turning it off. In other words, any time you start an instrument and stop it again, you have multiplied the signal by this. You have convolved it with this, which means that if there were a spectral line in the signal, it now looks like that. A little peak up there, peak of 1, but stuff. Now, the more you run the experiment, the narrower. But you remember, in optics, you had diffraction, right? That was exactly the diffraction you had. It was precisely the diffraction. But it tells you that you don't get to see what the star is doing. You get a sample, and the effect of sampling is the smearing out of all spectral lines into a smudge like that. Now, whether I sample first and get this, or whether I first cut it on and off and then do the sampling, it'll turn out to be the same. Because when I do the continuous one, I get a sine x over x form, and when I sum it over all the aliasing, this becomes that kind of a term. So there's no difference whether I think of first looking at the continuous signal, cutting on and off, and then sampling, or whether I sample and cut it on or off. It makes no difference. I get the same result, the same smearing of every single thing. The longer the run, the less wide the smearing is, but everything is smeared by that amount. So you can understand what it is when you make a long run in the lab. The longer you gather the data of some ongoing experiment, more accurate you can tell what you're doing. The shorter run, the less you can know, because it's all being smeared, every single line. And if two lines are close, and they're both, you'll only get to see one. Therefore, you've got to be far enough apart or have a long enough run to resolve the two separate peaks if you want to know there are two peaks. And it's a calculatable thing. So I'm trying to point out to you Fourier series and Fourier analysis explains what happens. Now what I'd found out is instead of taking 1 at each end, if I took the half I told you, I would come up with sine n omega over n sine omega, I think it's sine, there's a 2 there I think, cosine omega. The frequency is a little bit less, it's a little bit spread out, but that term will come down to 0 exactly. Well, I looked around in books. I finally found it in Zygmund's trigonometry Fourier series book, Fourier integral maybe, Fourier analysis I think. He called it a modified series. Well, it wasn't so important this time, but it's an example of what I've been preaching to you. I used my brain and said, well, why don't I put a half and let me see what happens? And I found that if I put a half just at the edge, just modify this thing, the window be a half, 1, 1, 1, a half. That small modification produced a big damping, but a slight broadening. The Gibbs phenomenon, same thing. Where the transition was very sharp here, those sigma factors widen it by a factor of 2. As you can see, if you run along this discontinuous function with a square averaging, you get like that. Because when you cut across there and begin to hit the zeros, all the way back here you're feeling some of the upper limit. Well, let me now say a couple other things about Fourier series. If a Fourier series is got a discontinuity of reasonable number, you remember there is an expansion, and the coefficients, ck, are the order of 1 over k. If the function has a has a derivative all the way through, then I could have integrated by parts, and I'll get an extra k below, and I'll get 1 over k squared. If my second derivative exists every place, meaning the first derivative is continuous as well as the function, I will get 1 over k cubed. Now, when I say continuous, you have to picture the Fourier series on a cylinder, and it's got to be periodic around the two ends. If you have a function like this, that is not periodic. This end doesn't look at that end. If the function is periodic, or at least, sorry, not periodic, if it is continuous, so the two ends match, then you got something. And the more smoothness you've got, the better. Well, the trouble with these, you see a corner here, right? If you were to pick you will have a raised cosine. Right? There won't be a discontinuity from here to here, as there is here. You will have, for these weights, wk, in place of the sigma factors, use these, you will have better convergence. Now, I might as well tell you a story. I don't have to rush out of class this time, how things really work. Incidentally, I pushed John into this by the following story. There was a story about von Neumann, who was visiting one time, and he's known to be a fabulous fast computer, and somebody set him up. Said, von Neumann, Johnny, do you ever think of so-and-so? The first case is easily done. The guys, of course, he answers first. Right? John starts to calculate the second case. He watches the guy a little bit. When John's getting around the second case, the guys, of course, he answers the second case such and such. Well, this has von Neumann mad. And he starts doing the third case in his head, which is enormously more complicated. And the guy watches. He's prepared by a week's computation earlier. He says to von Neumann, of course the answer to the third case is such and such, and walks off. And von Neumann is heard to say, how did he do it? How did he do it? How could he do it? It was a well-known story. The second well-known story, which I have to tell you, is one between Tukey and myself. I said, well, John, you're famous when your name is spelled with lowercase letter, like watt, ampere, volt, and sometimes Fourier. That's genuine fame. Before then, well, you're notorious, maybe, but fame when you got a lowercase letter. Well, the first story now. I was calculating for John. He had some very bad data, noisy stuff, and I was to calculate the spectrum. By the method used, there were some negative values. And it wiggled, just like that. I said to myself, that radar dish is not pulling energy out of the atmosphere. I don't care what you say. That's nonsense. And I had 3 runs. And I have, say, 3 or 4 days to think about it before I have to hand it to John, because John only comes in 1 or 2 days a week. He's a professor at Princeton. He works at Bell Labs a couple of days. And I notice that if I average these things 1 to 1, the consecutive data 1 to 1, it'll all be positive. Now, John has been a pain in the neck to me because he's so obviously smarter than I am. And if I say something, I got a little problem, he's got the answer like that. So I set him up, remembering von Neumann's story. I hand him this bad chart. I watch him. I can see him. Before he can pull himself together, I hand him the smooth one and say, of course, John, if you smooth it, you get this. I see his eyes bug a little bit. And before he can pull himself together, I give him the second one, the second smooth, the third one, the third smooth. He knows he's been had. He doesn't like it. He's worse than I am being egotistical. He's much more justifiable in his case. Well, he leans back in his chair. I watch him. I'm polite. I keep my mouth shut, let him think. In about 5 minutes, he creates the whole theory of windows and everything else like that. Boom. Because he couldn't stand a wise guy like me beating him. Well, this is one of the things that happens. When you've got some pride, you don't like coming in second. When you come in second, you don't blame the other guy, but you blame yourself. And driven to the thing by a guy like Hamming pulling out on him, he does this. Well, time goes on, and we have filters. This filter, by the way, the filter on the other side will look like these are frequencies along there, but there's leakage. This frequency comes through, all those little side loops are leakage into what you're looking through this window. You're seeing all the things through that window. You're seeing some frequencies up here coming in on top of that one. Well, we were working in a field where there was a very strong line over there, like 60 cycle, but it wasn't. It was another strong line. In which case, if that strong line were over here and leaking through one of the side ones, it would dominate what we're looking at. So Tukey asked the question, what kind of a window will have the minimum max lobe? How can I keep the max down? That's a Chebyshev's job. And where this thing has coefficients 1/4, 1/2, 1/4, this comes out to be 23, 54, 23. That's 25, 50, 25. This is not that. There's a little raised cosine. So it's a raised cosine on a platform. We use it a lot. We needed it. Well, one day, John, he's being compelled by the boss to write this stuff up in a book. He calls me from Princeton and says, Hamming, I want to name this filter after you. And I say, John, oh, come on now. A lot of people work this thing. He says, Hamming, you made a lot of small contributions. You're entitled to something. You some credit. I'm going to name it after you. I said, well, if you want to, John, go ahead. The book appears. The book he wrote, it's known as, and you can see it in print, lowercase h. It must be, if you're going to become at all famous, that the people with whom you work do it. I became famous to a great extent because I decided when I went to Bell Labs, insofar as I could, I would work with the interesting, smart people, and I would avoid the dummies. After some years of eating lunch with the math department where I was, and finding out they played games, they threw boomerangs, they flew kites, they were very fascinating, I wasn't learning anything. Furthermore, they were in some kind of mathematics. I wasn't, because I was involved in computing. So I started eating with a physics table where I had done some work with some physicists, and there were Shockey, Bratton Bardeen, and J.B. Johnson of Johnson Noise, and so on. I ate with them instead. They were doing important things. I helped them a lot. And one of my stories, I might as well tell you, more than a few times, they would say, such and such, such, such. I say, wait a minute. We ate in the restaurant with our placemat mats and paper. I'd grab and say, that is a simple differential equation you're talking about. Yep. I've then sketched the direction fields, and all the solutions go off to infinity that way. They can't. If that's a differential equation, that's what the solution must look like. I don't care what else you do. They all look like that. Ah, something wrong. Must be the equation. Well, yeah, I guess I forgot something. How valuable was that kind of a contribution? I say very valuable. I got them straightened out. I think that probably in total my most valuable contribution to Bell Labs was my ability to do elementary calculus like that. Yes, I did fancy mathematics, but you'll find that most of the mathematics I did was really down to earth and simple, just that I could do. Now, the people in the math department knew all the existence theorems of calculus and so on, but somehow they really couldn't produce it in novel, new situations. I could. I want to announce a proposition to you. And it's based upon not only that, but a great many other experiences. Talking to people who did great work and say, where did you learn that so-and-so? The proposition is very simple. That which you learn from others, as you're learning from me passively now, you could use to follow. That which you learn for yourself, you can use to lead. It's that simple. Most students are passively learning, and they can do quite well at following the professor, even bright ones. Those who have a little bit extra stubbornness and say, I'm going to understand this my own way, they have a chance of being the leaders. For example, Feynman. He's perfectly clear on it, and it was obvious when you met him. He didn't believe anybody at all, and I don't suppose if Jesus Christ came down to earth, he would have believed them. He had to think it through for himself. All of physics he recreated for himself. Is it surprising he got a Nobel Prize? Is it surprising he did lots of things? He really knew physics. He had thought it through for himself. And to some extent, I had done that in calculus. I had taught calculus a few times, but I had been impressed with it. And gradually, I said, well, this is too important. And every time I did an integral or something else, I would back down and try and look at the foundations behind it until I genuinely knew calculus. What you learn for yourself, you can use to be a leader. What you learn from others, you can use to be a follower. Which do you want to be? You can speak for yourself. My version is you are supposed to be a leader. That's my version. That's my version of what this course is about. How do I make you into leaders rather than followers? And one of the things is exactly that. How do I get you to digest things for yourself so that you will become a leader? And it is just that little extra. What you know, you go home and think about. You make it your own by digesting the thing until it is yours by your ways of thinking. Then it's available for you to use. If it's just by memory, you'll just remember what I said, and that isn't good enough. So you got the message? Very, very simple. It's those two things, luck favors prepared mind, or the other thing, learning the fundamentals, going a little bit further, not taking what's said, but thinking for yourself, and that is the difference between the first-class leaders and the second-class people. Next time, we'll take up another session on Fourier series, but with more stories. So see you Monday, and somebody's got some notes.